We're going to be covering chapter 10.2 through 10.3, and that will then mean this is our last lecture for this semester. The last things that we need to learn in this chapter on solutions are the principles of solubility. When we talk about solubility, we often encounter equilibrium, and that's why Lachatellier's principle is going to come up. I'll wait till we get there to say more. And then the last thing we're talking about are colligative properties. Now, colligative properties are properties that depend on the concentration of a solute and not necessarily on the nature of the solute. One of those colligative properties is osmosis and dialysis. We also have boiling point elevations and freezing point depressions as another example of a common colligative property. Okay, let's go ahead and get started with a little bit of review. And we're told a solution is made with 20 grams of sodium sulfate and 200 grams of solution, and we're asked what is the mass percent. Okay, we've got a calculation before us and equations or units, and for this we have an equation, our percent equation. Any percent equals your subject over your total times 100%. It's usually real easy to tell what your subject and what your total are. Our subject is the amount of solute, and the total is just that, the total amount of solution. And each of these are measured by mass. So we have 20 grams of sodium sulfate going on the top, there's our solute mass, and the 200 grams of solution going on the bottom, that is our total mass, or a 10% mass sodium sulfate solution. And again, make sure that you label these if you make these solutions, or if you're using one, make sure that you're using the one that's labeled correctly, because there can be a significant difference between mass and volume. Okay, a solution is made from 25 grams of sodium chloride and 100 grams of water. What is the mass percent? Again, any percent, subject over total times 100%, and our subject again is our solute measured by mass, and our total is just that, the total solution measured by mass. So on the top goes the 25 grams of sodium chloride, and on the bottom goes 125 grams of solution. That 100 grams of water is not the total. For a 20% mass sodium chloride solution. A beer is found to have 10 milliliters of alcohol and 200 milliliters of beer. What is the V/V percent? Again, any percent, subject over total, times 100%. The difference is now we're measuring those in volume. So we're looking for the volume of the solute. That would be the 10 milliliters of alcohol to go on the top. And the total volume, which is the 200 milliliters of beer going on the bottom. The beer does contain the alcohol, so that is the total for a 5% V/V alcohol solution. And real quick, I just want to mention that often a 5% by volume alcohol solution is only 4% by mass. And that's due to the 27% difference between the density of water and alcohol. And so there's a 27% difference between those two quantities. So this is why we need to make sure and identify how this is measured. Again, 27%, that's pretty significant. Next, how much glucose must be added in order to make 500 milliliters of a 10% mass volume glucose solution? Now, if you're given a percent, you're actually being given a conversion factor. And I'm going to go ahead and pull that out as a preliminary step. And this also helps me see that I'm using my units for this calculation. So good old step one, how much glucose? Well, what unit is going to go along with that? Well, as I look at my conversion factor, I see grams, so equals grams of glucose. Step two, only that 500 milliliters of solution has a single unit attached to it. And here comes step three. Let's get out of that initial unit. In step one, step two, and the beginning of step three should be a total no-brainer. On to the big question: can we go from milliliters of solution to grams of glucose? And as we look at that conversion factor, the answer is yes. And it also tells us where the numbers go. That 10 with the grams of glucose, and the cent with the mils of solution. So that means we need to add 50 grams of glucose to make that solution. And do note, this would be your first question if you were asked to make the solution. Well, you know the concentration, you know the volume. Well, how much solute do you need to measure out? Okay, how much of a 15% mass sodium iodide solution can be prepared from 60 grams of sodium iodide? Okay, we are still using our units, and I'm going to go ahead and pull that concentration term out as a conversion factor. Step 1, we're after how much solution, and I hope you can see why we decided on grams, because our conversion factor tells us that's what we're going to get into. Step 2, only that 60 grams of sodium iodide has a single unit. Now the beginning of step 3, let's get out of that initial unit. Here comes the big question, can we go straight from grams of sodium iodide to grams of solution? And our conversion factor sitting right there in front of us makes it easy to see that the answer is yes. So if the answer isn't jumping out at you, you're the one who really needs to pull out these conversion factors. Now eventually it'll all just become apparent to you, but it may take a little bit of practice. And we see where those numbers go, the 15 with the grams of sodium iodide and the 100 with the grams of solution. So 400 grams of solution can be prepared from that 60 grams of sodium iodide. Next, how much sodium bicarbonate? Actually, the official term is sodium hydrogen carbonate, but most folks call it sodium bicarbonate or bicarbonate of soda. And how much is needed to make 2 liters of a 20% mass volume solution? Well, let's pull out that conversion factor. And then on to step 1, how much sodium hydrogen carbonate? Only one of these numbers has a single unit attached, so there's step 2. And here's the beginning of step 3. And again, I hope you're seeing that step 1, step 2, and the beginning of step 3 are always really easy, and yet they get us halfway through the problem before we get to any challenges. I really hope that you're going to grab onto units and let them be your best friend. Because they will, but only if you let them. Okay, here comes a big question. Can we go straight from liters of solution to grams of sodium hydrogen carbonate? No, as I look at my conversion factor, I see I'm going to get to grams of sodium hydrogen carbonate from milliliters of solution. So there's my first move into milliliters of solution. Then from milliliters of solution, I can go to grams of sodium hydrogen carbonate. One milliliter, 10 to the negative third liters. Base 10 number, still going with the base unit. And that's 20 grams of sodium hydrogen carbonate per 100 milliliters of solution. For 400 grams of sodium hydrogen carbonate need to be added. Okay, a solution contains 34.2 grams of sodium hydroxide and 452 grams of water. What is the molality of the sodium hydroxide solution? Okay, well, we are still using our units, and I can't think of any preliminary steps. So, what are we after? And what are the units of molality? Moles per kilogram. Moles of solute per kilogram of solvent. Okay, that tells us for step 2, we're starting with one unit over another. And between grams of sodium hydroxide and grams of water, what's going to go on the top and take us to moles of sodium hydroxide? Grams of sodium hydroxide. That 4 grams of water is going to take us to kilograms of water. Okay, let's take care of our numerator. So out of grams of sodium hydroxide, can we go straight to moles of sodium hydroxide? We most certainly can. And there's our numerator. Taking care of our denominator, I'm going to put grams of water on the top. And can I go from grams to kilograms? We most certainly can. Molar mass of sodium hydroxide, 40.0 grams per each mole. And 1 kilogram, 10 to the positive third grams. And I come up with a 1.89 molal solution. Okay, to what volume should 150 milliliters of 5 molar acetic acid be diluted to give a 0.1 molar solution? Okay, well, I've got a dilution problem before me, so I know I'm using an equation, but I want to figure out what all that information is, so let me break out the equation to help, because I know those 3 pieces of information are 3 of these 4 variables. Using the units alone, I can tell I have a volume term in that 150 milliliters, a concentration term in the 5 molar, and another concentration in that 0.1 molar. So We're about halfway done with identifying what's what. Now we just need to know who's who. So to do that, we go to the two in the same measurement, the two concentration terms, and identify that the larger concentration is which? The concentration of the concentrate or the concentration of the dilute? The concentration of the concentrate. The lower concentration is actually the result of dilution, and almost part of the definition. Okay, what about that 150 milliliters? What's that? Well, it's of the 5 molar, which is concentrate, so it itself must be concentrate. And now from the process of elimination, we can tell we're after the volume of the dilute, and we can read the question carefully and see that is indeed what we're after. So we put the volume of the dilute on the left and divide out the molarity of the dilute, and here's the volume of the dilute isolated. And we've already identified these variables, so we're ready to plug them in. Note how all units cancel but milliliters. For 7,500 milliliters. Does our answer make sense? Well, our volume really went up a lot, didn't it? Well, our concentration went down a lot. Actually, our volume went up 50-fold because our concentration went down 50-fold. So I hope you're seeing that, yes, this is a reasonable and to be expected answer. Next, how many milliliters of 12 molar ammonia are needed to prepare 75 milliliters of 1 molar ammonia by dilution? Don't forget, you can always stop the presentation to do these problems on your own first. Very similar to what we did before, breaking out the equation so we know what our variables are, or at least what they potentially are, and then from the units that are attached, we can see what's being measured here. Then we compare the two in the same measurement, and again we have two in concentration, and the larger concentration is which? The concentrate. And what about that 75 milliliters? What is that? Well, it's of the 1 molar, which is dilute, so it must be dilute as well. And that tells us we're after the volume of the concentrate. Let's divide out the molarity to get the volume of the concentrate all by itself. And again, we just identified these 3 variables, so we're ready to go ahead and plug them all in. And I come up with 6.25 milliliters. Does our answer make sense? Well, what's with that small volume? Well, we need a small volume of the concentrated solution to get the larger volume of the dilute solution. So yes, this does make sense. I do expect my volume of my dilute to be larger than the volume of the concentrate. Now, I'm not sure if I've said this before, so let me try to clarify things. The concentration of the concentrate is the larger concentration, but the volume of the dilute is the larger volume. Okay, one more dilution problem, and the same approach. Let's break out our dilution equation, and then look through these variables and see if we can identify what they are. And now I have 2 volumes, and so again I compare the 2 that are the same, and so my larger volume would be which? The volume of the dilute or the volume of the concentrate? And remember, we achieve dilution by increasing the volume, so the greater volume is that of the dilute, and the lesser volume that of the concentrate. Okay, what about that 2 molar? Well, let me ask it this way. Is that 10 milliliters of the 2 molar or 40 milliliters of the 2 molar? Well, if we get stuck, well then let's just see what the question's asking for. Find the molarity when the sample is diluted. So if we're after the molarity of the dilute, that can't be what this is. It must be the other guy, the molarity of the concentrate. The molarity of the dilute is what we're after. So let's divide out the volume of the dilute. And here's the molarity of the dilute all by itself. And we just identify these 3 variables, so we're ready to go ahead and plug them in. And this time the 2 volume terms cancel to give me the appropriate concentration term. And does 0.5 molar seem like an appropriate answer? 1/4 of our original concentration? Well, since we increased our volume 4-fold, yes, we should decrease our concentration 4-fold. We're told concentrated phosphoric acid is 85% phosphoric acid by mass. The density is given, and we're asked for the molarity and the molality. Okay, well, first the molarity, and that would be in units of moles per liter. Step 2, we're going to take that 85% phosphoric acid by mass and identify the conversion factor that it gives us. 85% mass phosphoric acid solution. We build this the same way we built all of those percent conversions. Okay, we need to take care of both these units. So first, our numerator. So out of grams of phosphoric acid, can I go straight to moles? Be sure again, there's our most common calculation in all of chemistry. Then our numerator, out of grams of solution, can I go straight to liters? No. Let's see, grams is mass, liters is volume. That's why we're given the density term. So first from grams to cubic centimeters, which is a milliliter. I'm just going to kind of cheat and go from grams to milliliters. And then from milliliters to liters. The molar mass of phosphoric acid is 98.0 grams per each mole. The density, 1.689 grams per each milliliter. Again, 1 milliliter is exactly 1 cubic centimeter, so we can always replace those two. And 1 milliliter, 10 to the negative third liter, base 10 number still going with the base unit. And let's scratch out those units that cancel. So scratch the grams of phosphoric acid, scratch the grams of solution, scratch the milliliters of solution, circle the moles of phosphoric acid, and circle the liters just to make it jump out that much more. If we had made a mistake, we would have just caught it. And this year I have caught so many mistakes from my students where they set up their units but they don't go through and cancel them, and they end up inadvertently not having all their units canceled, giving them the units of their answer. And I come up with 14.6 moles per liter. Does that answer make sense? And yes. Okay, similar for the molality, only now it's moles per kilogram of water. We're still going to start with that 85%, so 85% mass phosphoric acid solution. We're still going to go on to step 3 and get out of grams of phosphoric acid. And yes, we're going to go straight to moles of phosphoric acid. That was nice and easy. Now, when we go to get out of grams of solution, can we go straight to kilograms of water? Let's be careful, that's grams of solution, not grams of water. But we can go to grams of water. And then from grams of water to kilograms of water. Molar mass of phosphoric acid still at 98 grams per mole. And now, in 100 grams of solution, how many grams of water would we have if it's 85% phosphoric acid? The remaining 15%. Okay, and 1 kilogram, 10 to the positive third grams, base 10 number, still going with the base unit. And when I hit equals, I get 57.8, and I would ask, does this answer make sense? And I told you before, the first time I hit this, got this answer, I thought I made a mistake. That's just way too big. But I had overlooked real quickly how with molality, we can actually generate a very small amount of solvent, and hence, with that very small denominator, generate a large number. So yes, this does make sense. It's molarity that has a cap of around 18. Okay, and next, a solution contains 124 milligrams of silver and 400 grams of solution. What is the concentration in parts per million? Well, that's the same setup as parts per 100, only we're multiplying by 1,000,000 instead of 100. And on the top is going to go our solute, the 124 milligrams, but I need to put that in a common unit with the solution mass, or the total mass. So let me go ahead and just convert that into grams. And my total, 400 grams of solution, and I didn't have to add in anything because that is my total. And even if I did have to add in that 124 milligrams, that would have been so far down in my significant figures it wouldn't have shown up. And that gives us a 310 parts per million silver ion solution. One more, a solution contains 0.0671 milligrams of the lead 2 ion and 2.50 kilograms of water. What is the concentration in parts per billion? Okay, similar to before, only now we're multiplying by 1,000,000,000. On the top is our subject, the solute, the 0.0671 milligrams of lead, but we need to convert that into a common unit with that 2.5 kilograms of water, so let's let that common unit be the base unit. So let me convert both into the base unit and flood them in, and now I get to 26.8 parts per billion lead 2 ion. I should still be asking, does my answer make sense? And to me, they look like they do. Okay, onto the principles of solubility. And we've seen in a previous chapter how some ions combine to form an insoluble precipitate. Well, we also saw that it was specific cations with specific anions. And so, first, let me talk about for something to dissolve, we're going to find that those ions end up being attracted towards the opposite sides of water. So here we can see how the chloride ion is attracted towards the positive side of water, and the positive ions are attracted towards the negative side of water. And so as long as they weren't held too strongly together, I should be able to pull them apart. And then once they're pulled apart, they can be surrounded by those appropriate portions of water, and that helps keep the ions separated from each other. So again, they end up forming what's called a hydration sphere, sometimes referred to as hydrated ions, where again, these ions are surrounded by the appropriate portions of water. So this is illustrating how these ions are compelled into solution and then surrounded by those appropriate portions of water, and then they travel around in these big groups where we may have many layers deep of water molecules with the appropriate end pointing in towards that central ion. And hopefully we can see that that actually does a lot to help keep those ions from recombining and coming out of solution. Now let me introduce you to the general solubility rule, and that's the simple statement like dissolves like, which is a simple way of just saying that we need like polarities in order for something to dissolve. Now, just like we saw above here, for anything to dissolve, there has to be an attraction between the solute and the solvent. And we saw above what that attraction was. And so, ultimately, polar molecules are attracted to other polar molecules, just like ions are attracted to the appropriate portions of these polar molecules. And it turns out that nonpolar molecules are attracted to nonpolar molecules. So that's what like dissolves like is essentially saying. Water does a good job of dissolving polar substances because it's a polar solvent. And let's say paint thinner, which is nonpolar, does a good job of dissolving nonpolar solutes. So again, polar compounds dissolve readily in a polar solvent, and nonpolar compounds dissolve readily in a nonpolar solvent. Just think about oil and vinegar not mixing, because the oil is nonpolar and the vinegar is polar. And in these test tubes, we can see that they form separate layers. Why would they form separate layers and not mix? Because one is polar and the other is nonpolar. I'm sure you've seen oil and vinegar do that as well. Okay, let me share some terms with you, as well as some concepts. And first we have the term solubility. Solubility, the ability to solubilize. This essentially describes the maximum amount of solute that can dissolve in a given amount of solvent, and this is normally stated under conditions of a certain temperature. So it might be 20 grams of sodium iodide dissolves in 100 grams of water at 25 degrees C. Well, why do I have to say in so much water? Well, if I had twice as much water, I could dissolve twice as much solute. Why do I have to state the temperature? Well, the temperature actually affects the solubility, and we'll talk about the why temperature affects solubility in a little bit. But I think we know that at different temperatures we're going to be able to dissolve different amounts. And again, we'll revisit that in a moment. The next term is saturated, and we have a saturated solution when we have the maximum amount of solute that can dissolve. And once we have a saturated solution, no more solute will dissolve, and so if you throw in some more of your solutes, it's going to remain there on the bottom of your container. Let me say it again. If you have a saturated solution and you add one more crystal, it's going to just go right to the bottom and it's not going to dissolve because we've got the maximum dissolved already. Now, when we have that situation, we actually have what's called dynamic equilibrium between the dissolved solute and the undissolved solute, meaning some of the dissolved solute is going to come back out of solution and attach to the solid, and then some of the undissolved solid will dissolve. So again, think of, now let me just say I've got a solution of sugar water, and I've got a little bit of sugar on the bottom in crystals that didn't dissolve. Well, some of those sugar crystals are actually dissolving, but at the same rate that some of the dissolved sugar molecules are undissolving. And actually, we can watch crystals grow by doing this. This is a dynamic, meaning in motion operation. Now, when you have reached equilibrium, really what that says is the rate of the forward reaction and the rate of the reverse reaction are the same, and so we wouldn't have any further change in the amount of dissolved solute. The picture on the left, we can see we can dissolve more solute, so this would be an unsaturated solution. But over here on the right, we can see some solid on the bottom, and so we have a saturated solution. And some of that solid is going into solution, but at the same time that some of the solute in solution is recrystallizing into the solid phase. So some of the dissolved is undissolving, some of the undissolved is dissolving. And again, this is a dynamic process, meaning it's in motion. It's not stagnant. It's not static. Okay, when we talk about equilibrium, we need to talk about Le Chatelier's principle, and Le Chatelier states that when you do something to perturb an equilibrium system, meaning the system already at equilibrium, that it's going to respond in a fashion to minimize that change. Now, the quick and easy way to think of this is, if you have an equilibrium system, then if you were to add to one side, it's going to shift the equilibrium to the other. Now, for adding something to have an impact, it can't be a pure substance, so it can't be a pure solid or a pure liquid. If you change something that has a variable concentration, like the concentration of something that's in solution or the partial pressure of a gas, that would change. That essentially that's adding or removing. So, so I just want to clarify that when you're adding something that's in equilibrium, we're talking about something that has a variable concentration. So adding more pure water isn't going to change something based on equilibrium water. Adding more pure solid sodium chloride isn't going to impact the equilibrium involving sodium chloride. Okay, now let's look at this equilibrium that happens when most solid solutes dissolve. We have that solute that's undissolved take a little bit of heat. So this is an endothermic process to get it to dissolve. And since heat is on the left, what's going to happen if we increase our temperature? Well, Le Chatelier says that the equilibrium is going to shift to the right, and hence we can get more solute to dissolve. And I think we've witnessed this. Normally heating something up and get more solute to dissolve. Now that's not the same for gaseous substances. So note here for the equilibrium where a gas dissolves. When a gas dissolves, we actually end up liberating some heat when it dissolves. So heat shows up on the right. Now, what then is going to happen if you increase the heat or the temperature of this system? Well, as you increase the temperature, you're adding to the right, and the equilibrium shifts to the left, and that gas tries to undissolve. Now, if you've ever opened up a warm beer or soda, you might notice that it really had a lot of gas that it released, and if it was a beer, it probably started spewing out. Just because it was warm. Because all that dissolved carbon dioxide was trying to undissolve. Now, the gas can have effect. Gas has a variable concentration, so that's not a pure substance. And so by increasing the partial pressure of the gas, let's say somehow I could increase the interior carbon dioxide in that beer, I'm going to now add to the left and shift the equilibrium to the right and have more of that gas that end up being dissolved. And this actually gives us the equation that the concentration of the gas is equal to a constant times the partial pressure of that gas. And we can see from this equation that the concentration of the gas that's dissolved is directly proportional to the partial pressure of the external gas above it. So if you were to double the partial pressure above it, you would double the amount that dissolves. Okay, on to colligative properties. And these are properties that depend on the concentration of the solute and not on their identity. The vapor pressure of a liquid is an example of a colligative property. The vapor pressure of a liquid decreases as the concentration of that liquid decreases. As you're adding more solute to that solvent, you would find that the concentration of the solvent is going down because now you have all of this solute there. And actually, let me use the concentration term of mole, the mole factor, or the mole percent, or the mole fraction. In other words, by adding more moles to somebody else, you're reducing the concentration or the mole fraction of that solvent. So if I had pure water, I would have a mole fraction of 1 for that water. If I start adding some solute, it's going to go down. And so as I add solute, the partial pressure of my water would go down. And by the way, that's any solvent, not just water. Osmosis is another example of an colligative property. And osmosis is the diffusion of water molecules through a semi-permeable membrane. Essentially what that means is we have a filter with holes so small that only water molecules can get through. Now, for diffusion, and diffusion always works this way. And if you're going into biology or the medical field, then you may already know this, or if not, you'll encounter this, that in diffusion, if something can diffuse, say, through your cell membrane, then it's always going to end up having a net migration from the higher concentration of that thing that can move to the lower concentration of that thing that can move. So if I have a higher concentration of sodium ions inside the cell than outside the cell, I'm going to have a net migration from in to out. And it would continue migrating until I would get to equal concentrations inside and out. Osmosis is the same phenomena, only it's water that can travel through. And so water is going to travel from the higher concentration in water to the lower concentration in water. And just as we had before, if you have a higher and higher concentration of solute, then that implies a lower and lower concentration of water. And that's actually the vapor pressure that's driving osmosis. Okay, now I'll introduce you to the term osmolarity, where osmolarity is simply the concentration and molarity of the osmotically active particles. Now, osmotically active particles are the things that are going to go into solution as individual entities. So let me give you an example here. For a 0.1 molar solution of sodium sulfate, I have a 0.3 molar osmolar concentration, or osmolarity concentration. Why is it 3 times as high? Because I'm going to have 3 particles. When the sodium sulfate dissolves, I'm going to have a tenth of, let's say I have a liter of it, I'm going to have a tenth of a mole of sulfate. And those 2, because I have 1 sulfate ion. But do note, I have 1 sulfate ion and 3 sodium ions. It's going to split into 3 ions. So again, if I have a 0.1 molar solution, it's actually 0.2 molar in sodium, because there's 2 of them, and 0.1 molar in sulfate, which means altogether a 0.3 osmolarity. Okay, on to osmotic pressure, and we're going to learn to calculate osmotic pressure. The simple equation for osmotic pressure is, there we go, pi, osmotic pressure, is equal to the number of moles of solute times the universal gas constant units of liter atmospheres per mole Kelvin times the temperature in kelvins times I over V. And I is that number of particles that your solute breaks down into. So previously, for the sodium sulfate, I would have been 3. Let's look at these examples at the bottom. For sodium chloride, it's 2, 1 sodium, 1 chloride. For magnesium sulfate, it's also 2, 1 magnesium, 1 sulfate. For calcium chloride, it's 3, 1 calcium and 3 chlorides for 3. And we already went over sodium sulfate also being 3. So I times the molarity is your osmolarity. Okay, so as we see, the osmotic pressure pi is equal to the concentration of your solute, if there's only one, times R times T times I. Now, if you have more than one, we have to add these all up. Okay, let me go back to reverse osmosis, and I just want to point out that reverse osmosis is the reverse of osmosis, meaning we're going to get water to travel from that, have a net migration to that membrane from the less concentrated to the more concentrated, the reverse of normal osmosis. And how can we get this to occur? By applying an external pressure greater than osmotic pressure. And if you get reverse osmosis where you are, say, meaning in your house or from some water source, this is how that reverse osmosis is achieved. The external pressure actually is from the pressure in your water lines. There's usually a pretty high external pressure in those water lines. Okay, let's look at an example where we're asked to calculate the osmotic pressure of a 0.1 molar solution of calcium chloride at 25 degrees C. Okay, we got a calculation before us, equations or units, and equations, the one we just saw. So let's break out that equation. Well, actually, I really don't see any preliminary steps, so let's break out that equation where the osmotic pressure is equal to the concentration of the solute times R times T times I. Concentration of the calcium chloride, the 0.1 mole per liter. Universal gas constant in units of liter atmospheres per mole kelvins. Our temperature in kelvins, temperature has always been in kelvins in this class, and I, for this case, is 3. And I hope that there's no question as to why I is 3. 1 calcium and 2 chlorides for a total of 3. And when I put this all on my calculator, I get 7.34 atmospheres. That's a significant pressure. Let's go back and look at these units and how moles cancel, liters cancel, kelvins cancel, leaving us solely with atmospheres. Okay, boiling point elevation and freezing point depression are also examples of colligative properties. And so you may know that if you have a solute solution that it tends to freeze at lower temperatures, freezing point depression, and it would boil at higher temperatures, boiling point elevation. Now, the equation for this is the change in temperature, delta T, for the freezing point depression would be equal to the colligative freezing point constant, K sub F, times your concentration in molality, times I, the same I. For the change in boiling point, very similar equation, only now delta T is equal to our colligative boiling point constant, times molality, times I. And K sub F and K sub B should not be expected to be the same. Do note here that K sub F for water is 1.86 degrees C per mole, whereas K sub B is less than a third of that at 0.52 degrees C per mole. And when we get to, I believe it's our next lab, or yes, I believe it's our next lab, we're going to be determining the molar mass of a solute based on the freezing point depression, and then we're going to be using an alcohol called tertiary butyl alcohol, which has a totally different colligative freezing point constant. We'll see that soon in the lab. Okay, let's see some examples. What we're going to do with this, we're asked to calculate the freezing point and boiling point of a solution that contains 50 grams of sucrose dissolved in 200 grams of water. Okay, well, our normal freezing point of water is 0 degrees C. And so our new freezing point will be that 0 degrees C minus the freezing point depression, meaning minus delta T. delta T is equal to K sub F times the molality times I. And our molality for this solution, well, we have 50 grams of sucrose, which we're going to convert to moles. We have 200 grams of water, which we convert into kilograms. And when I put this on my calculator, I come up with a 0.731 mole solution. Let me go ahead and plug that into that secondary equation. And now, what happened to I? There's K sub F, and there's the molality. What happened to I? Well, what's our solute? Sucrose, which is a sugar, which means it doesn't break down into multiple parts, into multiple units. If you got a mole of sucrose, it's going to dissolve and form a mole of particles. So I is 1. So let that be a little introduction to molecular solutes. They always have I equal to 1. So sucrose, alcohol, glycerin, anything, I would be 1. Okay, so that gives us a change in temperature of 1.36 degrees C. We're going to subtract that from 0 to get our new freezing point has been depressed to negative 1.36 degrees C. For the boiling point, we have our normal boiling point, 100 degrees C, plus the increase in temperature of boiling point elevation, for our increase in temperature. And our increase in temperature, delta T, is equal to our colligative boiling point constant times the molality times I. We already have the molality, and we also know that I is 1. So we multiply my colligative boiling point constant times my molality, and this time I only get 0.38 degrees C. So for water, we see a much more significant freezing point depression than boiling point elevation. Okay, we're asked to calculate the freezing point depression of 0.2 molar solutions of potassium nitrate and chromium-3 nitrate. Okay, well, delta T, K sub F, times molality, times I, and for the potassium nitrate, I will be 2. So 1.86 degrees C per mole times that 0.2 mole times the 2 gives us 0.74 degrees C. For the chromium-3 nitrate, I is equal to 4. 1 chromium and 3 nitrates for 4 ions. And so, twice the temperature depression. Okay, let's practice some of the things that we have learned. In a 25% volume alcohol solution, what is a solvent and how is it measured? And what's a solute and how is it measured? Well, the alcohol is measured by volume and the solution is measured by volume. The V and the V told us that. And why does ammonia exhibit hydrogen bonding? Because we have hydrogen directly bound, meaning covalently bound to one of those top electronegative elements, fluorine, nitrogen, and oxygen. And how does water hydrogen bond with itself? Do I have a picture? Well, it's going to be real hard to illustrate without a picture. Well, I'm sorry, I'll have to skip over that. And why does paint thinner not mix with water? Well, we know that water is polar, so what's that tell us about paint thinner? Non-polar. Okay, in this equilibrium system, what happens when the pressure of ammonia is increased? Well, following Lachatelier's principle, we're adding to the left, and it's going to shift the equilibrium to the right. And what would happen if the system is cooled? Well, heat is on the right, and I'm removing from the right, so it's going to shift in that direction to replenish it. So if you add to one side, it somewhat empowers it to push the other way. So it shifts the other way. If you remove from one side, you've kind of weakened it. It's going to be essentially overran from the other direction. So it's going to shift in that direction. So again, add to the left, shift right. Remove from the left, shift left. And what if a strong acid is added? Well, I don't see any acid as part of this reaction, so why is this question here? Well, we do see hydroxide, and that hydroxide would be removed by bringing in an acid. So that means I would be removing from the right again. So that also would cause a shift to the right. Adding a strong base, well, now I'm adding hydroxide, so I'm adding to the right, and that would cause a shift to the left. I always think of this like a push me, pull you. Add to one side, it's empowered to push the other way. Weaken the side, and it's overran from the other direction. And now what would happen if solid ammonium chloride is added? Well, as a solid one, I would say that's not going to do anything, but that actually would be a source of ammonium. I would expect it to dissolve and increase my ammonium, so I'm adding to the right, and so shift to the left. In osmosis, which in that direction does water travel through a semi-permeable membrane from the more concentrated side in water to the lower concentration in water. And what is osmotic pressure? Well, that's the pressure that's generated by osmosis, by this unequal concentration of water across that semi-permeable membrane. And what is reverse osmosis, and how does it occur? Reverse osmosis is just that. It's the reverse of normal osmosis. Osmosis is moving in the reverse direction, from less concentrated to more concentrated in water. And how does it occur? By applying an external pressure greater than osmotic pressure. And now, what solution would exert the greater osmotic pressure? 1 molar sodium chloride or 1 molar magnesium chloride? Well, the 1 molar sodium chloride would be 2 osmolarity in concentration, I is 2, whereas a 1 molar magnesium chloride is 3 osmolarity, I is 3. So the magnesium chloride. What about 5% mass lithium fluoride versus 5% mass potassium bromide? Well, this time both ions are going to split into just 2, so I is 2 for both of these. They're both 5%, so what's the difference? Well, lithium fluoride is a light mass compound, whereas potassium bromide is a heavy mass compound. So what's going to give you the greater number of moles? 5 grams of a small mass compound, or 5 grams of a large mass compound? And if you're getting stuck with that, then let's change it to something that's analogous but easier to relate to. What's going to give me the greater number of people? 500 pounds of big people or 500 pounds of small people? 500 pounds of small people. So the 5% lithium fluoride would have the greater number of moles and hence would exert the greater osmotic pressure. And now, what would happen to a blood cell if it's subjected to a solution low in solute particle concentration, like you threw it into pure water? Well, now you have a higher concentration of water outside than inside, and that means you would have a net migration from out to in, and that blood cell would swell and perhaps burst. And what if we went the other way and subjected to a solution high in solute particle concentration? Well, now we have a low concentration of water outside, and so we would have a net migration from in to out, and the cell would shrivel. Neither of these scenarios would be good for your blood cells. So that's why normally when you're given an IV, you would be given an IV with a solution that would have the same osmotic pressure as body fluids. And we may know that term is isotonic, the same osmotic pressure. Okay, now we're asked to calculate the osmotic pressure of a 0.0427 molar solution of iron 3 chloride at 20 degrees C. Okay, we only have one way to calculate osmotic pressure from our equation. Osmotic pressure is equal to the concentration of your solute times R times T times I. And we know what the concentration of the iron 3 chloride is. We know what R and T are. What about I? And I hope you're saying I has a value of 4. So we plug in that concentration, plug in my universal gas constant in units of liter atmospheres per mole kelvins, and plug in my temperature in kelvins, and there's I for 4.11 atmospheres. The other units for R is joules per mole Kelvin. When we're talking about energy, we'll be using that one. And if you join me in Chem 112, we'll definitely be using it again. Okay, calculate the freezing point and boiling point of a solution containing 100 grams of ethylene glycol dissolved in 200 grams of water. By the way, ethylene glycol is radiator fluid. And by the way, that's poisonous to most mammals. Okay, well, for the freezing point of water, our normal freezing point is going to be 0 degrees C, and we're subtracting delta T. Delta T, the colligative freezing point constant, times the molality, times I. Colligative freezing point constant is known, but molality is not. So it looks like we need to set up a third equation. And so, the molality, moles per kilogram. Let's get moles of the ethylene glycol, put it over kilograms of water, and I come up with a 8.06 molal solution. So now we're starting to generate a large molality concentration. Let's plug that into our secondary equation. Delta T is equal to K sub F times molality times I. And again, what happened to I? Ethylene glycol is a molecule, so it's only going to have one particle. And hence we can have a 15 degrees C freezing point depression. That's getting to be significant. Or negative 15 degrees C. We're asked for the boiling point too, so our normal boiling point plus delta T. It's not the same delta T because our colligative boiling point constant is different. Now we're going to have roughly about a third, a little less than a third of our change in temperature. Plug that into our primary equation. And it equals, for our new boiling point, of 104.19 degrees C. Okay, that concludes this lecture, and that means that this concludes all of our lectures. We do have some exam review, and that will be it for this class. And we also do have lab, depending on when you're doing this lecture versus when you're doing your lab. Okay, well, it has been my pleasure being your instructor, and I hope that you learned a lot about chemistry this semester.